All right, so let's start off this session. First of all, how was lunch for everyone? Was it good? Great, it was really awesome for me as well. Question, I'm a first-time NDC speaker. Is the food always this good? Or is it just Porto? Just Porto, okay. Then I came to the right place. Thank you very much. All right, welcome everyone. Thanks for coming to this session. My name is Ewald Verhoeven. I'm a test automation engineer from the Netherlands. I work for a company called Test Coders. More about that later. But first, I gotta admit, I'm very happy to see so many of you interested in testing, because who doesn't want to sit in for a 60-minute talk about unit testing, right? Because that is the most awesome part of development. Who agrees with me? You feel pressured into doing that. I know it. No, I'm kidding. But it is true, right? Unit testing is generally not the most exciting part of your day. I think most of you are developers, actually, right? Who's developer, engineer? That's literally every one of you. Cool. So yeah, it's not the most important, it is the most important part, if you ask me. But it's not the most exciting part of your day. And I hope to offer you something in this session that might actually get unit testing at least a little bit interesting, a little bit less boring, because yeah, it can be quite boring. I've seen some tests and some test suites, and I can imagine why you feel that way. But first, I'll introduce myself a little bit. I said I'm from the Netherlands, test automation engineer, but actually I want to introduce someone else. I didn't bring a co-speaker with me, but I want to introduce you to someone who I believe is the best test engineer of all time in the history of the field of test automation, and that is my son. Now I blocked his eyes, a bit funky actually, just for security reasons or privacy reasons. But I generally believe that he is the best test engineer out there. He turned 2 years old. We celebrated his second birthday last week, and he's super skilled in two practices in the practice of test engineering. And the first one is actually load testing. I think most of you are familiar with the term load testing. You may have performed a few of these yourselves. Specifically stress testing. I mean, the level of sophistication that goes in his test design and execution when testing the limits of my patience, that is just really up to professional levels, It's really ridiculous. And the other one is exploratory testing, and that's actually what we're going to talk about today. And as also an example of what you see on this picture here, is he just had a very successful session, as you can see. He found an alternative way to fit into his seat, like, feet up. He couldn't get out of it after this, but, let's forget about that. Sometimes test cases go wrong. That happens with exploratory testing. As you can see, he has quite a big bump on his head. That's because he just discovered gravity. Yeah, it's actually due to his sister. She's not as much of a test engineer, really, but she's like the enabler. She's like the scrum master, remover of impediments, And he was in his seat in that previous picture. He was in his seat. You can see the straps on his shoulder. She removed those straps for him, and then he just, dropped down. He just felt like, let's go for the ground, and he hit it quite hard. So those are my kids. They're animals. They're true dragons, masters of destruction, if you will. No, all kidding aside, I love them. But yeah, inspiration for me. As I said before, I'm in consulting, specifically the niche of test automation, unlike, I believe, most of you. So I'm not a developer, not a programmer. I'm not as skilled as you guys, but I do get hired by software companies to look at issues. And when I get hired, something broke, or something, typically something broke, or there are a lot of bugs, or there is something not right with quality. There is an issue there. There's maybe too much bugs, or releasing goes way too slow, stuff like that. So That's the companies I typically see. So when I talk about stuff from work, it's not that I think all companies are bad or all software development organizations are doing it wrong. Definitely not. There's a lot of you guys doing it very, very right. But I just want to share one common problem that I seem to come across when helping developers set up built-in quality, because that's what they're usually after. And this is one of the most common questions I get asked. And I know some of you are struggling with this question. Who has, okay, be honest, okay, who has asked himself this question in the last year more than once? All right, so that's, for the viewers, that's almost everyone, at least more than half of it. And there's good reason for it, because there's no one clear answer. When we're looking at unit testing, which we are today, there are a few things that we can implement, few things that we can look at. They're quite tricky as well, and I know most of you are using them. The most obvious one is coverage. Everyone's familiar with coverage, right? Don't need that. Cool. But there's an issue with coverage. As you can see, there are many, many forms of coverage. Yeah. Basically, I will narrow this down to two classifications, two main classes of coverage. And they're not the same. There's, on one hand, code coverage that I think all of you are familiar with. That's the one you referring to in your head right now. And there's test coverage. That's saying something else. And terminology might be confusing sometimes, and I will explain that a little bit later. But I want to go over both concepts real quick. Now, you said you're familiar with code coverage. Typically with code coverage, we have source code and we have test code, or we have a test suite somewhere. What code coverage does, it only looks at that source code part. It doesn't do anything basically with the test code. You know, you feed that to a runner or whatever, but your code coverage tool is only looking at your source code. What is your source code doing after you execute your tests? What's it doing? So when I play my test, it checks how much stuff, and we'll break that down a little bit, how much stuff got triggered when I executed my test suite. And then there is a percentage that's really cool to put up on GitHub in your batches and public repository if you have a very high coverage. Really nice to show off. But I want you to learn and to think about, what does that tell you? What have you learned when you look at that number? And therefore you need to dive into that coverage tool a little bit. Because what it actually says, it's a metric that says something about quantity, nothing about quality. Absolutely nothing. I could write a simple script, pretend that is a test, then run it, and it could still get me 100% code coverage. Because I could just call, entry points of my source code, and I could call everything. But code coverage does not look at your tests. If your tests are good, you could have written tests that don't include any assertions and still get a high coverage. I'm not saying it's useless. You should definitely use it. You should definitely use it, but I advise you to use it when you're in the process of writing your unit tests, right? So not when you're there and you think, okay, have I done enough? Check it out. Don't look at the metric. Don't look at the number. But usually these tools come with a report, like it says these lines, it highlights the lines that you didn't cover in red or that didn't run in red, and the lines that did run, it highlights those in green or something like that. Look at those reports. They're very, very useful, and I should encourage you to use that. Then there's another one, test coverage. I mentioned it before. Test coverage, instead of code coverage, actually uses the entire spectrum. It actually is a quantity of metric, a metric of quality. So it says something about how well is your test suite testing your source code. How well is it doing that job? Whoops. There are not many automation tools out there, but there is one that I'd like to mention. I'm not going into that in depth, but you can look it up, and that is mutation testing. Has anyone heard of mutation testing? Yeah, a couple of you have. Those who haven't, it's a tool that introduces mutants in your source code, then takes your test suite and runs it and see if it traces back to these introduced mutants. If you find all the mutants, if they got killed basically by the test, so if the tests fail as they should, then they are doing a good job. Now there's test coverage also for manual testing, but we're not talking about that today. So what we want ultimately is a high coverage. That's what we want. That's the goal here. Now, how do we get there? How do we design tests or a test suite that achieves that goal? It's not easy. And typically what we do, what I would do, is I start on the left of this graph that you see here. You start automating obvious cases, the things that are super clear, the easy ones. Then you'll move on to a bit more difficult ones, the things that you think like, I'm not sure if people are going to use this code this way or whatever, but it could be done. And you move to the middle, to the different cases. And that's usually where it gets really difficult after that, when we get to the edge cases. I mean, technically we could go on, and it's an infinitive amount of edge cases that you probably can come up with, and it gets really difficult. Right. So there's a technique, a test design technique that I've seen many developers apply, and it's a very well, it's a good technique. It's called error guessing. It basically builds off on the experience you have and the knowledge you have of a system, and therefore you get to design your test case. You think, oh right, that component might be a bit, shaky. That's where I'm going to attack it a bit more. That's a type of error guessing, an example of error guessing. There comes a problem. You will never get the full coverage because, as I said before, they're endless. Edge cases are endless. So you want to get as much edge cases as possible. There's another technique. In test engineering, it's called the decision table technique. And it's actually quite easy, and I'm going to illustrate this technique with a simple front-end system. So this is maybe not a login, or sorry, maybe not a unit test example. I will show you one later, though. But just to explain decision table technique, we have a login page. I know it says sign up, but it could say login. Doesn't really matter. And it has two input fields, and those could be either right or wrong, both of them, right? So the username could be either right or wrong. So if it's empty, it's wrong. If it's like some funny string, it's wrong. Pretty straightforward. You would write a table for that, and to determine what cases you should automate, or what tests you should automate. And when there's two conditions, or two properties in this case, it narrows down, or it boils down to 4 test cases to just cover all possible scenarios. Makes sense, right? Okay, not that difficult. Now there's another one. Now there's 3 conditions. I really had to look for this image though, because there are almost no login systems with 3 input fields, but I managed to find one. What happens then? So before, when there was 2 conditions, we had 4 test cases. Now there's 3 conditions, and we have to automate 8 test cases. I can see a problem here, right? It's still doable. I mean, you can still do this, but The problem is this with the decision table technique. Although it's very thorough and gives you a high coverage, this is the formula for calculating the amount of test cases you need to automate. And after I draw up this next table, I get to see more and more why you don't like unit testing. So X being the amount of test cases and being the amount of conditions that you can come up with. Because not all examples are as straightforward as that login page, okay? So I'm not even, let's if you can come up with with 10 conditions, that means like, do the math, like 1,024 test cases for one single unit? Nah, I'm not going to do that. Who of you is going to do that? Yeah, that's the one guy, yeah, I like you. We need to talk. I'm going to hire you. All right, I would go up to 3, maybe 4. After that, I'm out. You know, that's not my game now. That's where it gets boring. I don't want to do that. But I do want to get that high coverage, though. I've got an example. I know this is a Python syntax example. I'm not a .NET developer, as I said before. I think Python is very easy to read, has almost no syntax. A lot of downsides to it, but we have a simple unit test right here. The most simplest unit test in the world of testing. There's a function that does not need to be written, but for the sake of this presentation it is, and it's called addNumbers, and we're going to test that thing. It accepts an array of integers, and that's it. It provides us back, it returns an integer, and that's all the requirements there is. Now, we just looked at the decision table design technique. And I want you to think how many conditions, using the decision table design technique, how many conditions can you come up with for this extremely easy test, or simple test? I'll give you a few, all right? So, as you can see, we have a list, or an array, of 2 integers, and those are 2 positive integers. And it could be negative integers, it could be an empty array. So stuff like that, that's what we're typically looking for. So I've already given you 3. I will give you a second to think about how many other conditions that are either there or not can you think of? Who says more than 3? Right, okay. Who says more than 4? Yeah. Who says more than 5? 6. All right, 6, cool. 7? 7? Yeah, there's a few in the... Oh, nice. 8. No, yeah, still the same guy. Okay, thank you very much. So the ones that said 8, you're going to write 265 unit tests for this thing. Okay, theoretically. What I'm trying to illustrate is the fact that someone here, or the most of you say 3 or 4, and someone else thinks, okay, I can think of more stuff. That would result in people here, down here, writing only 32 test cases, and the other ones in the back are writing 260, 56 or something, I don't know. A lot more test cases, okay? There's a better way to do that, luckily for us. This is the way that we're doing it right now, and this is very specific, hence the title specific. It's explicit. If I change the input, I got to change the output. You know, 1 and 2 equals 3. If I say 1 and 3, then my test fails. 1. So I always have to alter 2 parameters here, or not even parameters. 2 inputs, 2 hard-coded things. Now, where property-based testing comes in is, first, it makes it more generic, and I'm going to show you the exact same example, but I refactored it into a property-based testing example, and that looks something like this. Now, this is hypothesis. It's just a Python library. Don't worry about it. I'll tell you what it does. It's funky stuff, but there is stuff for the .NET framework as well. There is fscheck. I haven't listed it. I'm sure you all can Google property-based testing, C# and property-based testing.NET. There's a great library called fscheck. Check that out. What it does, it describes the input rather than specifies the input, and it does that right there, and then passes it on to a parameterized test. Now, the most important part about this is actually the second part, the assertions part, the testing part. A test without assertions is not test. So the testing part, where we now describe the output as well, now it becomes fully parameterized. Now we can run this thing hundreds of times, thousands of times, probably in a couple seconds, with all kind of different inputs, because that's actually what a property-based testing framework does. It generates input based off that description that we had here at the top. Now, since we've described our output, we can also run assertions that actually give me feedback. If there's invaluable assertions that don't say anything, then it becomes pointless. So these things typically say something. Yeah, let's build a dragon, okay? Okay, so I'm going to give you an actual example that makes a little bit more sense, because that last one was just a refactored one that no one's ever going to use. So for this, you have to know we have written a simple sorting algorithm You're not ever going to do that, but let's say for sake, you have written a sorting algorithm. It's just a function or a class method, whatever. It accepts an array of integers again, but it also returns the sorted array. Yeah. Now this thing becomes a bit more specific because now I've also specified some other parameters. So that's something you can do with property-based testing. You can keep it very vague. Say a list of integers, that's still very vague. I could, massage it a little bit and tell it at least I want a minimum amount of items in that array of 2, or a maximum amount of items, or maximum amount of attempts, anything really. Sometimes that's useful. So an array of integers with a minimum of 2, and the actual cool thing here is in the bottom, where this is where we built that dragon, actually. Is first we check the type. That's the first assertion. Second assertion, it's a Python out-of-the-box thing. It basically checks that the input that we put into the test, or the content of that array, is the exact same content that comes out of the function when we call it, so that there's no data loss or trimming or deleting of duplicates or something like that. And the last assertion, that's really funny syntax. You should ignore that. But basically what it says is it checks if each item in the array is smaller than the next one. That's basically what it checks. Now this thing can run 200-300 times, somewhat like that. But let's run it. I actually wrote this algorithm, and let's run it. I want to show you the output. Docaris, here it goes. On the left, I know you can't read it, but I'll zoom in a little bit. On the left, you'll see the output of my test. And at the top, you'll see all the examples that it tried to run. Now, this is a failing test, you should know. This test is actually failing. And the reason it prints this out, because I put it in there. But I want to show you something is that interesting, is at the top, you see the examples it tries to run are quite long, quite extensive. Big numbers, big integers, negative, positive, everything. Big lists, a lot of items, and each run it seems to become a bit more simple, if you will. And that is because it is actually failing. And I know for a fact that from the second example right there, that starts with -16, the test fails, but it does not stop running. That's the sweet thing. It does not stop running until it knows for sure that it's falsifying, that it has a super easy example for you to show. So it keeps simplifying it and keeps running it until it finds the easiest example, and even that doesn't work. And then it shows you that at the bottom here in this case. That's called shrinking. As I said, complex example doesn't work. I make it simpler, I'll make it simpler until I find the easiest example I can find, and that doesn't work. Because 1 and 0 is not a sorted array, because I'm sorting in ascending order. You gotta know that. It was an ascending order I was looking for. So basically what it says, yeah, nice, Ewald, but you've written an algorithm that can't even sort that. That's pretty stupid. And the reason for that is because I didn't write any source code. I just returned the very same thing. I returned the list that it get and then didn't do anything with it. And that resorts into only one assertion that is actually failing here. So as you see, you can see there's my little test again, and it has the 3 assertions. And as you can see, there's a little arrow next to the last one. Now, you remember that last assertion was telling me whether or not the sort was listed, basically. That's one of the properties, a listed sort, a sorted list, sorry, or array. So it's basically telling me that list of 1 and 0, you cannot sort that, you idiot. It has the right type, yes, and it contains the same items, yeah, sure, but you can't sort it. Now that's pretty neat. There's something else I want to show you briefly about property-based testing, because I think we covered the basics right now. There's a little bit more. I'm not going to, teach you how to implement all of this, because I don't know fscheck, and that's, I think, what most of you are going to use if you're going to use property-based testing, which after today you will, of course. There's something else, because you are typically not writing source code that uses arrays of integers. you probably will be using something more complex. And I looked it up, every property-based testing tool and framework out there for any technologies has this ability of creating your own custom strategies in case of hypotheses. That's what they call it. It could be complex types, it could be interfaces. You could use basically anything as a descriptive input. So in this case, Python, again, doesn't work with interfaces, at least not explicit. It doesn't have an interface keyword. So I'm using a dog class, a model, sort of. And I'm writing a test right here. This is the test. And above that test, you'll see how I described the input. This is my description. Before we had just, we passed a list of integers in that given decorator. Now we're doing a custom strategy where I basically built my class. I gave it my two attributes that it has. A dog has a name, and it's of a certain breed. And I'm passing that to my test. Now I'm printing that out in the test, which is also funny. So this is not a test, even though it says it's a test, because a test should contain at least one assertion. Yes, yes, thank you. Great. So the funny thing is, and that's what I want you to remember, I'm giving it the name attribute as a text. So I'm not specifying anything else. I keep it very vague. I say text. Hypothesis here, do something with text, strings, and then it does something like this. So everything between the brackets was just the breed that it selected from a constant list, basically. And if you look at it, there's almost no normal characters in there, because I didn't specify anything else. I didn't say what characters to use, what not to use. It even tried an awful lot of spaces there. Okay, that's just stuff. These are edge cases, right? Who would think of any of these edge cases, by show of hands? Who would think to write a single, specific, explicit unit test to test something like pointer? There's no one raising his hand. Oh, that's the one. Yeah, you would think of it. Cool. Nice. That's what I mean. But these are edge cases that actually may cause trouble. This is where the bugs are. You've seen that graph before where I had the happy path, different path, and edge cases. The bugs are on the right side of that graph. They're not in the happy path, because that's what you were thinking about when you were writing your source code. They're not in the middle, typically, because that's something you can come up with error guessing. No, they're in the edge cases. That's where it becomes tricky. Right. I had this in the title of the talk as well. Now, I want you to be honest. Who of you came actually for the property-based testing stuff? Yeah, you're all good boys. And who of you actually, come on, be honest, came for the test reduction stuff? You thought, yeah, that's more interesting than anything else. Okay, so cool. Yeah, test reduction. There was a lot of noise around property-based testing in the beginning. It's actually been around for quite a long time. But everywhere I looked, basically, you get all kinds of claims that property-based testing leads to less testing. That's not entirely true, sorry. So that's the bad news. But the good news is, property-based testing actually can reduce your test efforts. The time that you, not test efforts, the time that you spend on unit testing. It also increases that coverage. That's the most important thing. That's why we want to do it, because it tests edge cases that we couldn't think about. We don't, but still it needs to be covered. And yes, it possibly, I said possibly explicitly, possibly decreases test code, not test cases, because actually it increases test cases, because that test that runs, if it runs successfully, in about 250 times or 200 times by default, in less than a second, like most unit tests, they're very quick. So technically, the amount of test cases that you run massively increases when you use property-based testing. However, you may be able to decrease your test code, not just because it's parameterized. If you haven't so, and you see that you have a lot of repeated tests, go please first parameterize. Makes it a whole lot easier, a little bit generic. But yeah, decrease test code, but not test cases. So let's get back to this question. When have you done enough? So now you have your coverage in place, and you run your property-based testing tool, and you think, cool, I got a 99% coverage. Then you run it again, and it may be 98 because, property-based testing doesn't always do the same thing twice. It's semi-random data, not exactly, but sort of. So at least you got a high coverage, cool, and that's nice. Whoops, that was the next one. But we're still looking at unit testing, and I want you to understand that property-based testing isn't something you always have to apply, necessarily. I think it's actually a great addition in some cases. I don't want you to think that, I've got all my tests wrong, and now I've got to refactor everything and apply property-based testing everywhere. That's not necessarily true. And that's another issue that I've come across quite often with development teams, is they don't really yet understand when to apply which technique, when to go all the way on unit testing and perhaps use property-based testing or mutation testing to check all of that, and when to, test lightly, because, there are cases where you can actually do that. You don't always have to do it. And for that, there's a model. Maybe you've heard of it, maybe you haven't. It's called risk-based testing. And that's where we look at probability of something, or a unit, or an entire component, or maybe an entire system to break. How likely is something to go, down, and the impact it will have on the end user or the organization, or, Now, I've sketched 4 blocks, let's say that there's a low impact and a low probability, then the risk level, of course, would be low. And then you need to assign actions and efforts to all of these levels. Now, I specifically have only 3 levels, as you can say, low, medium, high. I've seen organizations use this model, and it becomes it's kind of a pitfall to specify more levels, like there's low, there's very low, the medium rare, and high critical and all that. I would advise you to avoid getting too many levels, because you have to assign a certain set of test activities or quality activities to each level. Now, this is where I believe property-based testing, you could assign, for example, to the high risk level. If something has a huge impact if it goes down, and it's actually quite likely that that is going to happen, then I believe you want to test that very thorough, right? So 100% test coverage doesn't necessarily mean, or isn't always necessary. For the low risk stuff, I'm fine with just happy path, happy path test cases that cover that. Yeah. So that concludes most of my stuff. I want to recap a little bit before we go down, because I've seen there's still food left from lunch. I'm really anxious to get some more. If there's nothing you're going to remember from this talk, that's very sad. But I hope you at least remember this one thing: build a dragon. And what I mean by that, dragons. I've been mentioning it before as well. I like dragons. Dragons are absolute monsters of destruction. And they are very well in attacking stuff. And I want you to attack your stuff. I want you to try and break what you make. If you can break what you make, then you know exactly what to do when you're refactoring. If you can't break what you make, you've done a really good job. Then you don't need the coverage and the risk-based testing. Just make sure you can't break it. In order to do so, a property-based test is an absolute dragon, as I said before. It's very accurate, because that's what dragons are. Dragons are really accurate. There's this little series, I believe, what's it called? Game of Thrones. Anyone knows it? Yeah. I see some laughs. Okay. Only 4 people know Game of Thrones in this room. Oh, now it's more. Okay, cool. There's actually this one scene where this dragon queen is being attacked in an arena. You know what I'm talking about? I don't know which season or episode it was, but she's being attacked. She's in an arena. She's being protected by some of her guards, and then all of a sudden, her dragon flies into the rescue, and he starts, attacking all of her attackers. And it's really funny, actually, when he is so accurate in his level of destruction that he seems to know exactly which one are the good ones, the good guys, and which one are the bad guys. But to me, they look almost the same. They're both wearing masks and armor, and everyone is shouting and throwing spears and stuff. And no, he knows exactly. Oh, I need to eat that guy and throw that one away. That's why I think they are very accurate. That's where I learned that. And I want you to make a unit test that does exactly that, and apply it when necessary. Also learn from Game of Thrones, you don't always need dragons, you don't always want dragons. So risk-based testing for that, to determine when and what to need, and go build yourself a dragon. That was it. I'm going to thank you for your attention. Thanks for coming in. If you want to get the slides, I will put this repo public in about a second. You can always email me, and I'm also on Slack, especially the NDC space. I hope you had a good time. I hope you learned something and pick up something that you can take home with you. I enjoyed myself. Thank you very much.